Hello everyone, here is Khaled Omar, and in this video I am going to demonstrate Chapter 8 of the CCNP Enterprise Core 350-401, which is Open Shortest Path First, or OSPF. The contents of this video consists of 4 elements. The first one will be OSPF fundamentals, and the second one will be OSPF configuration. The third topic will be about default route advertisement, and the fourth element will be common OSPF optimization. Let's start by the OSPF fundamentals. Let me bring the highlighter or the pen. Let's start by how OSPF works. Actually, OSPF sends to neighboring routers link state advertisements that contain the link state and the link metric. And we will know later what is the OSPF metric. The received LSAs are stored in a local database called the Link State Database, or LSDB, and they are floated throughout the OSPF routing domain, just as the advertising router advertised them. Eventually, all OSPF routers maintain a synchronized and identical copy of the link state database for the same area, because in another video we will discuss how OSPF works with different areas, but for the purpose of this demonstration we are talking about the same area. So eventually all OSPF routers will maintain a synchronized identical copy of the link state database for the same area. The link state database provides the topology of the network, in a sense providing for the router a complete map of the network. Then when each router has a link state database, all OSPF routers run Dijkstra shortest path first algorithm, or the SPF algorithm. Why? To construct a loop-free topology of the shortest paths. So once each router in the OSPF domain has a link state database, consists of link state advertisements, it runs Dijkstra shortest path first algorithm to construct a loop-free topology of shortest paths. OSPF dynamically detects topology changes within the network and calculates loop-free paths in a short amount of time with minimal routing protocol traffic. Each router sees itself as the root or top of the SPF tree, the spanning tree path, or the shortest path first tree, the shortest path first tree, or SPT. And the SPT contains all network destinations within the OSPF domain. The shortest path first tree differs for each OSPF router, but the link state database used to calculate the shortest path first tree is identical for all OSPF routers. Let's give an example here where 4 routers, router number 1, R1, and R2, R4, and R3, they are connected in this way. R1 connected to R3, R1 connected to R2, R2 is connected to R4, and R4 is connected using serial link to R3. The cost of each path is here 10, here 10, here 10, and here 20. Let's take it from R1 perspective. R1 to reach R2, or the subnet that is attached to R2, can go through this way or through this way. The Dijkstra shortest path first algorithm chooses the loop-free path and the shortest path to each destination. So R1 will think about here the cumulative metric or the cumulative cost is 10 plus 10 equal 20. And this path is 10 plus 20 equal 30 plus 10 equal 40 plus 10 equal 50. So this path is 20 and this path is 50. Ospf, or the Dijkstra shortest path first, will choose this shortest path with the lowest cost or the lowest metric, the lowest cumulative cost. And similarly, between R1 and the subnet attached to R4, R1 will go through R2, 10 plus 10 plus 10 equal 30, and through R3, 10 plus 20 plus 10 equal 40. So Ospf will choose this path because it has the lowest metric. So if you will draw the spanning tree, the shortest path first tree, sorry, I don't know why I'm talking about spanning tree, because maybe they have some similarities in the concept. The loop-free, I mean, topology. So R1, from R1's perspective, the topology will be looks like this. R1 connected to R2, R2 connected to R4, but the link between R3 and R4 is not considered because it makes the links has a high metric. So the loop-free topology and the shortest passes will be looks like this. The shortest path first tree from R1 perspective looks like this. Similarly, from R4's perspective, the shortest path first tree will look like this. As we mentioned in this slide, each router sees itself as the root or top of the shortest path first tree. And the shortest path first tree contains all network destinations within the Ospf domain, as here. So from R4 perspective, the link between R1 and R3 is missing, is not presented in the spanning shortest path first tree from R4 perspective. And from R1's perspective, the shortest path first tree ignores the link between R3 and R4. There is a difference in connectivity to the subnet 10.3.3.0/24 network from R1 shortest path first tree and R4's shortest path first tree. From R1 perspective, the serial link between R3 and R4 is missing. From R4's perspective, the Ethernet link between R1 and R3 is missing, as we mentioned here. This one is missing, and this one is missing. From R1's perspective and R4 perspective, respectively. The shortest path first trees gives the illusion that no redundancy exists to the networks, but remember that the shortest path first tree shows the shortest path to reach a network and is built from the link state database, which contains all the links for an area. During a topology change, The shortest path first tree is rebuilt and may change. So, OSPF provides scalability for the routing table by using multiple OSPF areas within the routing domain. Each OSPF area provides a collection of connected networks and hosts that are grouped together. Actually, OSPF uses a two-tier hierarchical architecture, where Area 0 is a special area known as the backbone area, to which all other areas must connect. If we will have here Area 0, the backbone area, all other non-backbone areas must be connected to the backbone area. Those are non-backbone areas. So Area 0 provides transit connectivity between non-backbone areas. What this means, if this area wants to reach destinations in this area, it must pass through Area 0. So non-backbone areas advertise routes into the backbone area, then advertise routes into other non-backbone areas. So the advertisements will be from the non-backbone area to the backbone area, and from the backbone area to the non-backbone area. As shown here, the two-tier hierarchical area structure of OSPF. We have here Area 12, which is a non-backbone area connected through R2 to the backbone area, Area 0, and Area 0 is connected to Area 34 through R3, which is a non-backbone area. So Area 12 routes will go to the backbone area, and the backbone area will send these routes to the other non-backbone area. Similarly, from Area 34 to Area 12, it will go through Area 0, the backbone area, and then to the other area. And Area 0 routes will go simply to each non-backbone area, as mentioned in the arrows in the figure. So, Area 12 routes are advertised to Area 0 and then into Area 34. Similarly, Area 34 routes are advertised to Area 0 and then into Area 12. Area 0 routes are advertised into all other OSPF areas. The exact topology of the area is invisible from outside the area. So, from Area 12 perspective, it doesn't know the exact topology of Area 34. And similarly, Area 34 doesn't know the exact topology of Area 12, while still providing connectivity to routers outside the area. This means that routers outside the area don't have a complete topological map for that area. Why? Which reduces OSPF traffic in that area. When you segment an OSPF routing domain into multiple areas, it is no longer true that all OSPF routers will have an identical link state databases. However, all routers within the same area will have identical copy of the link state database inside that area. The reduction in traffic, in routing traffic, uses less router memory and resources, and therefore provides scalability. Actually, a router can run multiple OSPF processes. Each process maintains its own unique database and routes learned in one OSPF process are not available to a different OSPF process without redistribution of routes between processes. What this means? It means that if we will have a router here, it can run multiple OSPF processes, and each process is different from the other one, and routes learned in one OSPF process are not available to a different OSPF process without using redistribution. Redistribution means to send routes from one OSPF process to another OSPF process, or from one routing domain to another routing domain. The OSPF process numbers are locally significant and don't have to match among routers. This router can use OSPF process number 1, and this router can use OSPF process number 2, and they can be OSPF neighbors. So it is not a mandatory that the OSPF process between routers should match. Running OSPF process number 1 on one router and running OSPF process number 1234 will still allow two routers to become neighbors, as we mentioned here. Let's see how the inter-router communication happens between OSPF routers. OSPF runs directly over IPv4 using its own protocol number 89, which is reserved for OSPF by the Internet Assigned Authority, Numbers Authority, or IANA. So OSPF uses protocol number 89, and OSPF uses multicast where possible to reduce unnecessary traffic. You have to keep these two addresses in your mind, because in the packet capture that we will do in an example later in this presentation, we will find out that OSPF uses two multicast addresses. And these two multicast addresses are 224.0.0.0.5. And this for all shortest path first routers. And the MAC address looks like that. It ends with 505. It means all routers running OSPF should be able to receive these packets. There is another multicast or OSPF multicast address. It aims for sending to all designated routers. So the IPv4 address is 224.0.0.6, and the MAC address is similar to the first one, except it ends with 06. The last hexadecimal digit is different in the MAC address. And it aims for communication with designated routers, uses this address. So for OSPF multicast addresses, we use this one and this one. This one for all shortest path first routers. All routers running OSPF should be able to receive these packets. And this multicast address aimed for designated routers, sending to all designated routers only, not all shortest path first routers. Let's see what are the types of packets used by OSPF. Actually, within the OSPF protocol, there are 5 OSPF packet types used in the communication. The first packet is called hello. The second packet is called database description, or DBD or DDB. You can use DBD or DDB for database description. The third packet is link state request, or LSR. The fourth packet is the link state update, or LSU, and the last packet is link state ACK, or LSA. What is the function of each packet? For the hello packet, these packets are for discovering and maintaining neighbors. These packets are sent out periodically on all OSPF interfaces to discover new neighbors while ensuring that other adjacent neighbors are still online. It's like the heartbeat. It detects, discovers, and maintains neighborship between OSPF routers or OSPF interfaces. The database description. These packets are for summarizing database contents. Packets are exchanged when an OSPF adjacency is first being formed. After sending hello and forming an adjacency or neighborship between the two routers, they start to exchange the database between them. And these packets are used to describe the contents of the link state database. What about the link state request? These packets are for database downloads. When a router thinks that part of its link state database is stale, it may request a portion of a neighbor's database by using this packet type. What about the link state update, the fourth packet type? These packets are for database updates. This is an explicit link state advertisement for a specific network link and normally is sent in direct response to an link state request. What about the link state acknowledgement or LSA? It's different than the link state advertisement because they have the same acronym, link state ACK or acknowledgement. These packets are for flooding acknowledgement. These packets are sent in response to the flooding of LSAs, thus making flooding a reliable transport feature. When we will capture packets, OSPF packets, we will see all these 5 types of OSPF packets. You have to keep them in your mind. So let's discuss the OSPF hello packets. OSPF hello packets are responsible for discovering and maintaining neighbors. In most instances, a router sends hello packets to all shortest path first routers address, which is 224.0.0.5. The following table lists some of the data contained within an OSPF hello packet. So the hello packet contains some fields or data, and these fields are: the first one is the router ID, the second one is authentication options, the third field for area ID, interface address mask, interface priority, hello interval, dead interval, designated router and backup designated router, active neighbor. Let's describe each one of these fields. Router ID, the router ID, a unique 32-bit ID within an OSPF domain. It's something that uniquely identifies the OSPF router in the OSPF domain. The authentication options. This field allows secure communication between OSPF routers. Why? To prevent malicious activity. Options are none, clear text, or message digest 5, MD5 authentication. So if you will use authentication option on one router, you have to use the same authentication options on other routers so they can secure the communication between them. Why? To prevent any malicious activity. The third field is the area ID. The OSPF area that the OSPF interface belongs to. It is a 32-bit number that can be written in dotted decimal format, like 0.0.1.0, or in decimal format like 256. The fifth field of the OSPF hello packet is the interface address mask. The network mask for the primary address for the interface out which the hello is sent. The interface priority, the router interface priority used for DR elections. In the broadcast, we will discuss this type of elections in another slide, but remember that the hello packet contains interface priority that is used for the election of the designated router. The other field is the hello interval, the time span in seconds that a router sends out hello packets on the interface. After how long the router should send a hello packet out of the interface. This is the hello interval. The dead interval, the time span in seconds that a router waits to hear a hello from a neighbor router before it declares that the router is down. Designated router and backup designated router, the IP address of the DR and the backup designated router or BDR for the network link. The active neighbor, a list of OSPF neighbors seen on the network segment. A router must have received a hello from the neighbor within the dead interval. You have to keep in mind these OSPF hello packet fields. Let's discuss the first field, which is the router ID. The OSPF router ID, or RED, is a 32-bit number that uniquely identifies an OSPF router. In some OSPF output commands, the neighbor ID refers to the RED. The terms are synonymous. The RED must be unique for each OSPF process in an OSPF domain and must be unique between OSPF processes on a router. And the router ID is represented in the dotted decimal format. So it's like 10.1.1.1. An OSPF neighbor. Let's discuss the neighbors and the types of neighbors. An OSPF neighbor is a router. There are no types of neighbors. They are OSPF neighbors. So an OSPF neighbor is a router that shares a common OSPF-enabled network link. So if we will have a router here, and the router here, and the router here, and they are sharing the same network link, they can be OSPF neighbors. OSPF routers discover other neighbors via the OSPF hello packets. An adjacent OSPF neighbor is an OSPF neighbor that shares a synchronized OSPF database between the two neighbors. This is called adjacent OSPF neighbor. Each OSPF process maintains a table for adjacent OSPF neighbors and the state of each router. The following table describes briefly the OSPF neighbor states. This is one of the most important topics you have to keep in mind. If we have here a router, OSPF router, and another OSPF router, and they are sharing the same network link, there are neighbor states, OSPF neighbor states, that happens between these two routers before becoming fully adjacent or Ospf neighbors. The first Ospf state is down, and its description is that this is the initial state of a neighbor relationship. It indicates that the router has not received any Ospf hello packets. Before sending any hello packets between the routers, they are in the down state. The second Ospf neighbor state is attempt, and this state is relevant to non-broadcast multi-access networks that don't support broadcast and require explicit neighbor configuration. This state indicates that no information has been received recently. But the router is still attempting communication. No information received, but the router is attempting. That's why it's called attempt. Initialize state. This state indicates that a hello packet has been received from another router, but bidirectional communication has not been established. This means that one router sent a hello packet, but still the other router didn't send a hello packet. The two-way state, its bidirectional communication has been established, and if a DR or BDR is needed, the election occurs during this state. Remember this. The election of the DR, designated router, or the BDR, backup designated router, occurs during the two-way state. And it means that this router sent a hello packet and the other router sent another hello packet. The other state is EX start or exchange start. This is the first state informing an adjacency. Routers identify which router will be the master or slave for the link state database synchronization. So once they send the hello packets, they will choose or identify which router will be the master and which router will be slave. Why? For the link state database synchronization. They will start in the other state, which is exchange, to exchange the database description packets. So during this state, routers are exchanging link states by using database description packets. The other state is loading. The link state request packets are sent to the neighbor. Here, for the exchange, they start to send database description packets. And loading, it means that the link state request packets are sent to the neighbor. Link state request, asking for the more recent link state advertisements that have been discovered but not received in the exchange state. And the last state is full. Neighboring routers are fully adjacent. These are the 8 Ospf neighbor states: down, attempt, initialize, two-way, EX start, exchange, loading, and full. Now let's discuss the designated router and backup designated routers. What are these two types of routers? In a multi-access networks, such as Ethernet LANs, and frame relay, which allow more than 2 routers to exist on a network segment, Such a setup could cause scalability problems with OSPF as the number of routers on a segment increases. Let's assume that this is an Ethernet link and there are routers here, OSPF routers, sharing or connecting to the same segment. We have here 8 routers, and we can have n routers or a lot of routers. In case the number of routers on a segment increases, OSPF will have scalability problems. Why? Because additional routers float more LSAs or link state advertisements on the segment, and OSPF traffic becomes excessive as OSPF neighbor adjacencies increase. Let's give an example here. If 4 routers share the same multi-access network, 6 OSPF adjacencies form, along with 6 occurrences of database flooding on a network. What this means, if we have 4 routers here sharing the same network segment, this router will form with this router neighbor relationship, and the second, third, fourth, fifth, and sixth. So 6 OSPF adjacencies form, no other possibility here. And this will cause 6 occurrences of database flooding on the network. What should we do in this case? First, let's see how the full mesh adjacencies occurs between the 4 routers. As we mentioned, 1, 2, 3, 4, 5, and 6 adjacencies. In case of 4 routers sharing the same network segment, this occurs in a multi-access network. This is the physical topology, and this is the logical topology. The number of edges formula is n multiplied by n minus 1 divided by 2, where n is the number of routers, and it is used to identify the number of sessions in a full mesh topology. So let's give an example. If we have 5 routers were present on a segment, the number of OSPF adjacencies will be 10 for that segment if we will follow this formula. Continuing the logic, adding 1 additional router would make 15 OSPF adjacencies on a network segment. So if we have 6 routers, we will have 15 OSPF adjacencies on the network segment. Having so many adjacencies per segment consumes more bandwidth, more CPU cycles, and more memory to maintain each of the neighbor states. Let's give here a diagram. When the number of routers increases, the number of sessions per segment increases in this way. So if you have 5 routers here, the number of OSPF sessions will be 10. In case of 6, it will be 15, and so on. Once the number of routers increases per segment, the number of sessions or OSPF adjacencies increases. What should we do in this case? And to overcome this inefficiency, OSPF overcomes this inefficiency by creating a pseudonode or virtual router to manage the adjacency state with all other routers on that broadcast network segment. A router on the broadcast segment, known as designated router, assumes the role of the pseudonode. The DR, or the designated router, reduces the number of OSPF adjacencies. This is the main objective of the designated router, to reduce the number of OSPF adjacencies on a multi-access network segment, because routers only form a full adjacency with the designated router and not with each other. The DR also is responsible for flooding updates to all OSPF routers on that segment as updates occur. The following figure demonstrates how using a DR simplifies a 4-router topology with only 3 neighbor adjacencies. Let's give, without DR, we will have 6 adjacencies. But with DR election, we will have only 3 adjacencies. If the DR were to fail, Ospf would need to form new adjacencies, invoking all new link state advertisements, and could potentially cause a temporary loss of routers. So what to do in this case? In the event of DR failure, a backup designated router becomes the new DR. Then an election occurs to replace the backup designated router. So on a network segment, multi-access network segment, we should have a designated router and a backup designated router. If the designated router fail, the backup designated routers becomes the new DR, and then new election will replace the BDR. To minimize the transition time, the BDR also forms full OSPF adjacencies with all OSPF routers on that segment. Why? To minimize the transition time from the BDR to a new DR. When a router becomes a backup designated router, it forms full OSPF adjacencies with all OSPF routers on that segment. And in case the DR fails, the BDR immediately will be a DR and keeps the full OSPF adjacencies with all OSPF routers on that segment. Let's see how the network prefix advertisements with DR segments. Step number 1, by the way, if we have more than 2 routers on a segment, the other routers will be called DR other. So in case we have 5 routers, we will have a DR, a BDR, and DR others. This DR send a link state update to the DR and the backup DR. The DR responds with a unicast ACK or acknowledge, and then in step 3, the DR floats this update to all SPF or shortest path first routers. So in this case, the address will be 224.0.0 yes.6. Why? Because it is all DR routers, designated routers, which means the DR and the BDR. This is the multicast address. The acknowledgement from the DR to the DR other will be unicast. This is the acknowledgement, or else link state acknowledgement. This is the link state update, and this is the link state ACK. The final step will be link state updates to all SPF routers, shortest path first routers. And the address, the multicast address will be 224.0.0.5, as we mentioned earlier. So the DR and BDR process distributes link state advertisements in the following manner. All OSPF routers, DR, BDR, and DR other on a segment form full OSPF adjacencies with the DR and BDR. As an OSPF, step number 2, as an OSPF router learns of a new route, it sends the updates link state advertisement to all DR routers through the multicast address 224.0.0.6, which only the DR and BDR receives and process. The DR sends a unicast acknowledgement to the router that sent the initial link state update. Then the DR floats the link state advertisement to all the routers on the segment via the all shortest path first routers through the multicast address 224.0.0.5, as we mentioned in this slide. Now let's move to the next content or the next topic in this video, which is OSPF configuration. The configuration process for OSPF resides mostly under the OSPF process, but some OSPF options go directly on the interface configuration submode. So some configuration will be under the OSPF process. Other options can be under the interface configuration submode. The command router OSPF process ID, which is a global configuration command, defines and initializes the OSPF process. The OSPF process ID is locally significant, but is generally kept the same for operational consistency. What this means? It means that the routers on a segment can use the same or different OSPF processes and still form OSPF adjacencies. Actually, OSPF enables on an interface using two methods. The first one will be an OSPF network statement. The second one will be interface-specific configuration. So to enable OSPF on an interface, you can use the network statement under the OSPF process or the interface-specific configuration under the interface configuration submode. Let's start with the OSPF network statement to enable OSPF on an interface. The OSPF network statement identifies the interfaces that the OSPF process will use and the area that those interfaces participate in. So you have to enable OSPF on an interface and assign the area ID for that interface. The network statement matches against the primary IPv4 address and the net mask associated with an interface. A common misconception is that the network statement advertises the network, which is not happening, into OSPF. In reality, the network statement is selecting and enabling OSPF on an interface. It is not advertising the network but in reality it is enabling and selecting OSPF on an interface. Later, the interface is then advertises the interface is then advertised in OSPF through the link state advertisement. The link state advertisement, yes. The network statement uses a wildcard mask, which allows the configuration to be as specific or vague as necessary. The selection of interfaces within the OSPF process is accomplished by using the following command or the following router subcommand. To select an interface, use the network statement and the IP address, wildcard mask, and associate this interface to a specific area ID using this command. And in an example, we will see all these commands, the network statement or interface specific subcommand. If the IP address for an interface matches two network statements with different areas, the most explicit network statement that is the longest match preempts the other network statements for area allocation. What this means? It means that if the IP address for an interface matches two network statements, if for example this router has IP 10.1.1.1/24 and the network statement IP is 10.1.1.0 with wildcard mask 0.0.0.255 and another network statement 10, and by the way this is for example in area 5, and the other network statement is 10.1.1.0.0.0 and in area 0. The most explicit network statement that is the longest match preempts the other network statements for area allocation. So this one will preempt the other network statement for area allocation. So OSPF will be enabled in this interface in both cases, but the area ID, the area allocation will be the longest match. So it will be in area 0. The connected network for the OSPF enabled interface is added to the OSPF link state database under the corresponding OSPF area in which the interface participates. So when enable OSPF on that interface, the connected network, this one, is added to the link state database under the corresponding OSPF area, which this interface participates to. So this subnet or this network will be in area 0. Secondary connected networks are added to the link state database only if the secondary IP address matches a network statement associated with the same area. Let's give an example here that will help you to understand the concept. The following scenarios explain potential use cases of the network statement for a router with 4 interfaces. Let's assume that we have a router here, one interface, first interface, second interface, third interface, and fourth interface, and this is router number 1. This is giga 0/0, 0/1, 0/2, and 0/3. This one is associated with IP address 10.0.0.10/24. This interface associated with an IP address 10.0.10.10/24. This interface 192.0.0.10/24, and this interface 192.0.0.10/24. Let's see the network statements that will be used in this example. The configuration in the following example enables OSPF for area 0 only on interfaces that explicitly match the IP address in table 80-5, which is this table. So under the OSPF process, number 1, there are 4 network statements. The first one enables OSPF on this interface. The second network statement enables OSPF on that interface. The third network statement, which uses the exact IP address with wildcard mask zeros, will enable OSPF in that interface. And the last network statement will enable OSPF on that interface. So we used 4 network statements. You can minimize the network statements if you would like by modifying the wildcard mask. So for example, you can use network statement network ten 10.0.0.0 wildcard mask 0.255.255.255 and in area 0. This network statement will enable OSPF in those 2 interfaces. Why? Because they start with 10. And in this example, we use 10.0.0.0, and the wildcard mask will check the first octet only. So the first octet must match for an interface IP address to be enabled, so OSPF will be enabled. The following example displays the OSPF configuration for area 0 using network statements that match the subnets used in table 8-5, which is this table. If you set the last octet of the IP address to 0 and change the wildcard mask to 255, the network statements must match all IP addresses within the /24 network. So if we use this network statement, OSPF will be enabled on any interface starting with 10.0.0, and similarly in the other network statements. There is another example for the network statements to enable OSPF on all 4 interfaces, as we mentioned here. in this example. So the network statement must match the first octet because the wildcard mask is 0.255.255.255. So using only these two network statements, OSPF will be enabled on all the 4 router interfaces. And they will all belong to area 0. There is a last example to enable OSPF on all router interfaces to use this network statement. Network 0.0.0.0 wildcard mask 255.255.255.255 area 0. This will enable OSPF on all routers interfaces. The second way to enable OSPF is to use interface-specific configuration. And this second method for enabling OSPF on an interface for iOS is to configure it specifically on an interface using the following interface subcommand: IBOSPF and the process ID, area, and the area ID. Secondary is none means that if the interface has a secondary IB, the OSPF will not be enabled on that interface. So this method also adds secondary connected networks to the links database unless the secondary is none option is used. This means that if an interface has two IP addresses, primary IP and secondary IP, and you enabled OSPF on that interface using interface-specific configuration, without secondary nonce, OSPF will be enabled on two IP addresses or the two connected networks. With secondary is none, it will be enabled only on the primary network connected. This method provides explicit control for enabling OSPF. However, the configuration is not centralized and increases in complexity as the number of interfaces on the routers increases. Let's assume that we have a router with 15 interfaces and you are enabling OSPF using interface-specific configuration. So you will have to type 15 commands like this for each specific interface. So this increases the complexity. If a hybrid configuration exists on a router, interface-specific settings take precedence over the network statement with the assignment of the areas. What this means? It means that if you enabled OSPF through interface-specific settings and you enabled OSPF on the same interface using network statement with different areas, the interface-specific settings take precedence over the network statement. The following example provides a sample interface-specific configuration. Under the interface with an IP address, you enable OSPF and associate the interface to a specific area. Let's see how to statically set the router ID. By default, the router ID is dynamically allocated using first, the highest IP address of any up loopback interfaces. If there are no up loopback interfaces, then the highest IP address of any active up physical interfaces becomes the red when the OSPF process initializes. The OSPF process selects the router ID when the OSPF process initializes, and it does not change until the process restarts. So in case of changing router ID, you have to restart the OSPF process. And we will show you how to restart the OSPF process using the clear IPOSPF process command. Interfaces changes such as addition, removal of IP addresses on a router are detected when the OSPF process restarts and the router ID changes accordingly. So to choose the router ID first, static configured router ID. If no static configured router ID is configured, then step 2, to choose the router ID, choose the highest IP of any up loop back interface. If no loopback interfaces are up, then the third option will be the highest IP of up physical interface. The OSPF topology is built on the router ID, and setting a static router ID helps with troubleshooting and reduces link state advertisements when a router ID changes in an OSPF environment. The router ID is 4 octets, like the IP address, in length, but generally represents an IP address that resides on the router for operational simplicity. However, this is not a requirement. How to configure the router ID statically? You can use this OSPF process subcommand, router ID, and give a router ID. And to let the router ID be used, you have to restart the OSPF process using this command, clear IP OSPF process, in the privileged mode. This command restarts the OSPF process on a router so that OSPF can use the new router ID. Let's discuss what are passive interfaces. Actually, enabling an interface with OSPF is the quickest way to advertise a network segment to other OSPF routers. However, it might be easy for someone to plug in an unauthorized OSPF router on an OSPF-enabled network segment and introduce false routes, thus causing havoc in the network. Making the network interface passive still adds the network segment into the link state database, but prohibits the interface from forming OSPF adjacencies. It advertised the network into the link state database, but prohibits OSPF adjacencies on that interface. So a passive interface does not send out OSPF hellos and does not process any received OSPF packets. To choose an interface as a passive interface, the following command under the OSPF process makes the interface passive. You can use this router subcommand, passive, and choose the interface ID. And the following command makes all interfaces passive, which is passive interface default. And then to allow for an interface to process OSPF packets, the following command is used, no passive interface ID. If you used passive interface default, it will make all interfaces as passive interfaces. If you want to make exception, use no passive and specific interface. Let's discuss what are the requirements for network adjacencies. If we have a router here and a router here, and they are OSPF routers, and they need to be OSPF neighbors. What are the requirements for the network adjacency on this link? The following list of requirements must be met for an OSPF neighborship to be formed. The first one, router IDs must be unique. If this one will be used 1.1.1.1, this one shouldn't use 1.1.1.1. It shouldn't, because router IDs must be unique between the two devices and for the entire OSPF routing domain. So each router in the OSPF routing domain must have a unique router ID. The second one, the interfaces must share a common subnet. If, for example, this one has an IP address 10.1.1.1/30, this one should be 10.1.1.2/30. If it is another IP other than this one, .4 for example, .5 for example, they will not be neighbors. So the interfaces must share a common subnet, which is here 10.1.1.0/30. The MTU of the interfaces must match. If this interface use MTU 1500, this one must use MTU 1500. The area ID must match for the segment. If this interface belongs to area 0, this one must belongs to area 0. But this interface can belongs to another area, or for example area 1, but on the network segment. That's why we say the area ID must match for the segment, this segment. The other requirement, OSPF hello and dead timers must match for the segment. For this interface, the hello timer and the dead timer must match the hello timer and dead timer for this interface on that segment. The designated router enablement must match for the segment. Authentication type and credentials, if any, must match for the segment. If you use authentication, OSPF authentication, the type and credentials must match on the segment. The area type flags must match for the segment, and we will discuss later what are the area type flags, which is, for example, stub area, not so stubby area, and so on. Let's give an example here for the OSPF configuration. Let's assume that we have 4 routers, router number 1, router number 2, router number 3, and router number 4, who are sharing this link and IP subnet 10.123.4.0/24, and all routers belongs to area 0. This interface 4.1, 4.2, 4.3, and 4.4, which means 10.123.4. This number. And each router has a connected subnet to be advertised via OSPF. Here 10.1.1.0/24, here 10.2.2.0/24, here 10.3.3.0/24, and here 10.4.4.0/24. Let's go to the GNS tree to configure this example. So we will add 4 routers, router number 1, router number 2, router number 3, and router number 4, sharing the same network segment. And we will assume that we are having here BC1, BC2, BC3, and BC4. Let's connect the routers through fast Ethernet 00 to the switch, fast Ethernet 00 to the switch, fast Ethernet 00 to the switch, and fast Ethernet 00 to the switch. And then Ethernet 2/0 to the PC, Ethernet 2/0 to the PC, Ethernet 2/0 to the PC, and so on. Let's start the 4 routers. And then assign the IP addresses 10.123.4.1/24, .2, .3, .4. And then here 10.1.1.0/24, 10.3.3.0/24, and here 10.2.2.0/24, and here 10.4.4.0/24. Let's assign the IP addresses quickly. For router number 1, configure T interface fast Ethernet 0/0 IP address 10.123.4.1.255.255.255.0, no shutdown. Interface Ethernet 2/0 IP address 10.1.1.1.255.255.255.0, no shutdown. And similarly on the other routers. We are just configuring the IP addresses as in the example. And later we will enable Ospf on the interfaces using network statements and interface specific configuration. Let's finish router number 3. Interface fast Ethernet 0/0 IP address 10.123.4.3.255.255.255.0, no shutdown. Interface Ethernet 2/0 IP address 10.123.4.4.255.255.255.0. Oh, overlaps. Sorry. IP address 10.3.3.1 255.255.255.0. No shutdown. Let's go to router. Let's first check. Yes, correct. Let's go to router number 4. Then let's enable OSPF on all the interfaces of each router, and all these interfaces will belong to area 0. So this will be in area 0.
Have a new mail.
Let's go to router number 1, but before we start, let's start capture.
Have a new mail.
And then we will see how the packets are exchanged between routers. Let's keep it here and go to router number 1. Router OSPF 1. To enable a OSPF on this interface, we have to use network statement, network 10.123.4.1. For example, we will use different network statements and different interface specific commands. 0.0.0.0 area 0, and the network 10.1.1.1 0.0.0.0 area 0. Now we enabled OSPF in these two interfaces. Let's go to router number 2. Router OSPF. We can use number 2, but for consistency we will use 1. Network 0.0.0.0 255.255.255.255 area 0. This will enable OSPF on all interfaces. Let's check the Wireshark. And as you can see here, hello packets. Let's filter by OSPF. Hello packets, database description, link state request, link state update, and link state acknowledge. Now router number 1 is in full adjacency with router number 2. To check, do show IP OSPF neighbor. As you can see, we are on router number 2, and the neighbor ID is 10.123.4.1, which is router number 1. Let's go to R3. Router OSPF 1. Let's give it a router ID 3.3.3.3 and enable network 10.123. Forget about this. 10.0.0.0 0.255.255.255 area 0. This will enable OSPF on all interfaces of router 3 because it starts with 10. Let's hit enter. On router number 4, we are going to use the interface specific configuration. So let's go to interface fast Ethernet 0/0 IB OSPF 1 area 0. Let's go to the other interface. Interface Ethernet 2/0 IB OSPF 1 area 0. And save the configuration. Let's check the packets that are advertised. All of them are the 5 types of packets used by OSPF. Hello, number 1, database description, link state request, link state update, and link state acknowledge. Let's see which router is the designated router and which router is the backup designated router. So let's go to R1, show IB OSPF interface brief. As you can see here, router number 1 on fast Ethernet 0/0 is the DR. And if we want to check which one is the BDR, show IB OSPF neighbor. You will find out that router number 2 is the BDR, router number 3 is DR other, and router number 4 is DR other. Let's configure the router ID for each router as like that. 1.1.1.1 for router number 1. Three to 3 for router number 3. We already configured this one. 2.2.2.2 for router number 2. To make it easier for us to understand, 4.4.4.4 for router number 4. Let's go to router number 1. Conf T router OSPF 1. Router ID 1.1.1.1. Look what it will tell you. Reload or use clear IB OSPF process for this to take effect. Let's go to this mode, clear IB OSPF process. Hit enter. It will restart the OSPF process. Let's save the configuration. Let's go to router number 2. Interface, fast Ethernet. Sorry, what are we doing? Router OSPF 1. Router ID 2.2.2.2 and clear IB OSPF process. Yes. Let's go to router number 4 because router number 3 is already configured. Router OSPF 1. Router ID 4.4.4.4 and clear IB OSPF process. Yes. Let's check the Wireshark. Same packet types. Now let's see which router is the designated router. Show IB OSPF neighbor. They are still in the two-way state, and here in the AX start. So let's wait a little bit until full adjacencies will be accomplished. Now the DR is router number 4, and router number 3 is DR other, router number 2 is DR other, and our router number 1 should be the BDR. Show IV OSPF interface brief. Router number 1 is DR other, but still the neighborship is accomplished in the accomplishment phase. Now router number 4 is the DR, and router number 3 is the BDR. And why? Because we will discuss this actually in another slide, that the BDR and DR has a default priority of 1, as you can see here, priority 1, but the highest router ID will be the DR, and the second highest router ID will be the BDR. The other router will be DR others. Okay, so now we have router number 4, DR, router number 3, BDR, router number 2, DR other, router number 1, DR other. Let's go to the packet capturing, and we will do a modification on, for example, router number 1. Let's go to router number 1 and add a loopback interface. Loopback 1, IP address 10.5.5.5.255.255.255.255, and then enable OSPF on this interface. IP OSPF 1 area 0. Look what will happen here. Router number 1 sent, let's stop this. Router number 1 sent link state update to the DR and BDR multicast IP address to 224.0.0.6. Then the DR, router number 4, sent the link state update to all shortest path first routers through the multicast address 224.0.0.5. And then the DR others, router number 2 and router number 3, the DR and BDR, the DR other sent to the DR and BDR link state acknowledge, and the BDR sent to all shortest path first routers link state acknowledge. Any changes in the network will happen something like that. Now let's go back to our slides. Bring the pen. Let's discuss default route advertisement, OSPF default route advertisement. OSPF supports advertising the default route into the OSPF domain. The default route is advertised by using the following command. It's OSPF router subcommand. Default information originate, option to use always, option to use a metric with metric value, optional to use metric type with type value. If a default route does not exist in a routing table, remember this, if a default route does not exist in a routing table, because it should be presented in the routing table if you will use default information originate only. But if a default route does not exist in a routing table, the always optional keyword advertises a default route even if a default route does not exist in the routing information base or the routing table. In addition, the route metric can be changed with the metric value option, and the metric type can be changed with the metric type value option. Let's give an example here where this figure illustrates a common scenario where R1 has a static default route to a firewall where the traffic goes to internet that is connected to the internet to provide connectivity to other parts of the network. For example, R2 and R3, R1 advertises a default route into Ospf. So to go to internet, R1 should advertise a default route to other routers. So let's give an example here through GNS3. Sorry. Yes, the following example provides relevant configuration on R1. Notice that R1 has a static default route to the firewall 10.100.64.1.2 to satisfy the requirement of having the default route in the routing information base. Let's go to, for example, our GNS scenario. We will assume that R1 has, let's first check R2 routing table, show IP route Ospf. It learned about the network attached to each router through Ospf. Let's assume that R1 is connected to a firewall and we need to advertise a default route to all other routers. So without a static default route, we will go to router OSPF1 default information originate always and hit enter. Let's go to R2, check the routing table. As you can see, a default route advertised to the other routers, and it is considered as a type 2 external OSPF route. But in most cases, you use only default information originate, and before using this command, you have to use IP route 0000.0.0.0 and the next hop. Let's say 100.1.64.1, the firewall. Hit enter and use the default information originate only. This will take all the traffic from the other routers that is destined to the internet to R1 and from R1 to the firewall. Let's go back to our slides. As you can see here, in router 1, IP route and 00, this is the static default route. And then under the router, the OSPF process, use default information originate. So first you have, if you don't have a default static route, use the always option. But usually you should have a static default route, so you don't need to use the always option. As we saw, The following example provides the routing tables of R2 and R3, and as you can see here, the default
Have a new mail.
route is presented as external OSPF route. External OSPF route. Now let's discuss the third or the fourth element of this video, which is common OSPF optimization, and we will start by link costs. Actually, the interface cost is an essential component of Digestra's shortest path first calculation because the shortest path metric is based on the cumulative interface cost, that is the metric from the router to the destinations. OSPF assigns the OSPF link cost, that is metric, for an interface by using the following formula. The cost equals reference bandwidth divided by the interface bandwidth. The default reference bandwidth is 100 megabit per second. And the following table provides the OSPF cost for common network interface types using the default reference bandwidth. So in case we have a T1 serial link, the OSPF cost is 64. In case you have Ethernet, the OSPF cost is 10. Fast Ethernet, 1. Gigabit Ethernet, also 1. 10 gigabit Ethernet, also 1. You have to keep this in mind. The default settings. The interface cost using default settings. There is a note here, notice in table 8-8 that there is no differentiation in the link cost associated with a fast Ethernet interface and 10 gigabit Ethernet interface. Changing the reference bandwidth to a higher value allows for a differentiation of cost between higher speed interfaces. Making the value too high could cause issues because low bandwidth interfaces would not be distinguishable. The OSPF link state advertisement metric field is 16 bits, and the interface cost cannot exceed 65,535 value. And under the OSPF process, the following command changes the reference bandwidth for all OSPF interfaces associated with that interface. Under the OSPF process, you can use AutoCost reference bandwidth and change it to a specific value in megabit per second, and the default is 100 megabit per second. If the reference bandwidth is changed on one router, the reference bandwidth should be changed on all OSPF routers to ensure that shortest path first uses the same logic to prevent routing loops. It is the best practice to set the same reference bandwidth for all OSPF routers. The OSPF cost can be set manually using the following interface subcommand: IB OSPF cost, and choose a value from 1 to 65,535. While the interface cost is limited to this value, because of link state advertisement field limitations, the path metric can exceed a 16-bit value because all the link metrics are calculated locally. What this means? It means that if you changed the interface cost to a higher value, the total cost of the path can exceed the 16-bit value because the link metrics are calculated locally on each router. Let's discuss another option for OSPF optimization, which is failure detection. A secondary function of the Ospf hello packets is to ensure that adjacent Ospf neighbors are still healthy and available. This is one of the functions of the Ospf hello. Ospf sends hello packets at set intervals based on the hello timer. Ospf uses a second timer called the Ospf dead interval timer. So Ospf uses the hello timer and the dead interval timer, which defaults to 4 times the hello timer. If the hello timer is 10 seconds, the dead interval timer is 40 seconds. Upon receipt of a hello packet from a neighboring router, the Ospf dead timer resets to the initial value and then start to decrement again. If an Ospf hello packet is sent, this dead interval timer will resets to the initial value 40 and then start to decrement again. 39, 38, 37, another hello 40, 49, 30, 39, 38, 37, 36, another hello after 10 seconds, of course, then it will resets. If a router does not receive a hello before the dead interval timer reaches 0, the neighbor state is changed to down. The Ospf router immediately sends out the appropriate link state advertisement reflecting the topology change, and the shortest path first algorithm processes on all routers within the area. That's why we use the concept of area, because any change occurs in the area domain, the shortest path first algorithm should be processed on all routers within the area. The hello timer. The default Ospf hello timer interval varies based on the Ospf network type. Ospf allows modification to the hello timer interval with values between 1 and 65,535 seconds. Changing the hello timer interval modifies the default dead interval too. The Ospf hello timer is modified with the following interface subcommand. This interface subcommand IB Ospf hello interval and give a value in seconds. The dead interval timer can be changed to a value between 1 and 65,535 seconds. The Ospf dead interval timer can be changed using the following interface subcommand. IB Ospf dead interval and a value in seconds. Note here, always make sure that the dead interval timer setting is greater than the hello timer setting by logic to ensure that the dead interval timer does not reach 0 between hello packets. If, for example, the hello timer is 10 and the dead timer interval is 5 seconds, before sending the hello, the router will be considered as down because it didn't receive hello before this go to 0. To verify the Ospf timers from the iOS command line interface, use the show IB Ospf interface command. It will tell you what is the hello timer interval and the dead timer interval. Use show IB Ospf interface, include timer -line. Let's give an example here. Let's go to router number 1. Show IB Ospf interface, include timer line. Without this, include timer. As you can see here, the hello interval is 10 seconds, the dead interval is 40 seconds. But to show the interface, hyphen line. Yes. Show IP OSPF interface include timer hyphen line. This gives you the hello timer on each interface and the dead interval timer for each interface. Let's go back to our slides. There is a note here. Hello and dead interval timers must match for OSPF neighbors to become adjacent. So if you have a router here and a router here and they are sharing the same network segment, the hello timer here and dead interval timer must match the hello interval here and dead timer interval here to be neighbors or OSPF fully adjacent. The DR replacement. The DR and BDR rules for a broadcast network consume CPU and memory on the host routers in order to maintain states with all the other routers for that segment. So, placing the designated router and backup designated router rules on routers with adequate resources is recommended. So you have to choose a router with good resources, CPU and memory, and assign it the role of the designated router and the backup designated router. So how to choose or to place the DR in the network? By elections, choosing the designated router elections. The DR and BDR election occurs during OSPF neighborship, specifically during the last phase of two-way neighbor state, and just before the EX start state. When a router enters the two-way state, it has already received a hello from the neighbor. If the hello packet includes a router ID other than zeros, 0.0.0.0 for the DR and BDR, the new router assumes that the current routers are the actual DR and BDR. Any router with OSPF priority of 1 to 255 on its OSPF interface attempts to become the DR. By default, all OSPF interfaces uses a priority of 1. So to choose the priority, first, the routers place their router ID and OSPF priorities in their OSPF hellos for that segment. Routers then receive and examine OSPF hellos from neighboring routers. If a router identifies itself as being a more favorable router than the OSPF hellos it receives, it continues to send out hellos with its router ID and priority listed. If the hello received is more favorable, the router updates its OSPF hello packet to use the more favorable or preferable router ID in the DR field. OSPF deems a router more preferable if the priority for the interface is the highest for that segment. So to elect a DR, there are two options: the interface priority and the highest router ID. If the priority is higher than 1, that router should be the DR. If they have the same priority but different router IDs, the highest router ID will be the DR. If the OSPF priority is the same, the higher router ID is more favorable. Once all the routers have agreed on the same DR, all routers for that segment become adjacent with the DR. As we mentioned earlier, then the election for the BDR takes place. The election follows the same logic for the DR election, except that the DR does not add its router ID to the BDR field of the hello packets. The OSPF DR and BDR rules cannot be preempted. What this means, if you change the priority, for example, for a specific interface, the DR will still be the DR and the BDR will still be the BDR until you restart the OSPF process. So the OSPF DR and BDR rules cannot be preempted after the DR BDR election, as we did in the lab on GNS3. Only upon the failure or process restart of the DR and BDR does the election start to replace the rule that is missing. There is a note here. To ensure that all routers on a segment have fully initialized, OSPF initiates a wait timer. When OSPF hello packets don't contain a DR router for a segment, the default value for the wait timer is the dead interval timer. This is the default value. Once the wait timer has expired,
Have a new mail.
a router participates in the DR election. The wait timer starts when OSPF first starts on an interface, so that a router can still elect itself as the DR for a segment without other OSPF routers. It waits until the wait timer expires. So the easiest way to determine the interface rule is by viewing the OSPF interface using the following command, as we did in the configuration, show IP OSPF interface brief. It will tell you which router is the DR, which router is the BDR, which router is the DR other. So DR and BDR replacement. How to choose which router is the DR and how to choose which router is the BDR. As we configured, we didn't choose the priority, but we changed the router ID. So modifying a router's router ID for DR placement is a bad design strategy. A better technique involves identifying the interface priority to a higher level than the existing DR has. The priority can be set manually under the interface configuration using the following command: IPOSPF priority, and give it from 0 to 255. And remember that setting the interface priority to 0 removes that interface from the DR-BDR election immediately. So let's go to our GNS lab. Here we have router number 4 as the DR and router number 3 as BDR, and router number 1 and router number 2 are DR others. If we want to make router number 1 the DR, let's go to router number 1, configure terminal, interface, fast Ethernet 0/0, IPOSPF, priority 10. Show IPOSPF interface brief, still DR other. Let's go to router number 4, clear IPOSPF process, enter. Now let's check again. Let's wait a little bit until the full adjacency occur. Now fast Ethernet 0/0 is the BDR. Why show IB/OSPF interface fast 0/0. The priority here is 10 and the state is BDR. Let's go to router number 3. Clear IB/OSPF process. Wait a little bit. Show IB/OSPF interface fast Ethernet 0/0. Now the priority, as you can see, is 10 and the state is DR. So now router number 1 became the designated router. And who is the BDR router? Show IB/OSPF interface brief. Show IB/OSPF neighbor. The BDR is router number 4 because it has the highest router ID between the other 3 routers, and priority is still 1 for each one of them. Let's go back to our slides. Raising the priority above the default value 1 makes that interface more favorable compared to interfaces with the default value. And as we did in the example, we made R1 always DR by changing the priority to 10, and it became the DR router or the designated router. Last thing we will discuss here, maybe not the last thing, but it is before the last thing, or maybe the last thing, the OSPF network types. Different media can provide different characteristics or might limit the number of nodes allowed on a segment. Frame relay and Ethernet are a common multi-access media. Because they support more than 2 nodes on a network segment, the need for DR exists. Other network circuits, such as serial links with HDLC or point-to-point encapsulation, don't require a DR, and having one would waste router CPU cycles. So in case of multi-access networks, the DR is required, but in case of point-to-point or the serial links that uses HDLC or point-to-point, there is no need to use a DR. The default OSPF network type is set based on the media used for the connection and can be changed independently of the actual media type used. Cisco's implementation of OSPF considers the various media and provide 5 OSPF network types as listed in the following table. The first type is broadcast, the second type is non-broadcast, the third type is point-to-point, the fourth one point-to-multipoint, and the fifth one is loopback. The broadcast default setting on OSPF enabled Ethernet links. Non-broadcast default setting on OSPF enabled frame relay, main interface, or frame relay multi-point sub-interfaces. Point-to-point default setting on OSPF enabled frame relay point-to-point sub interfaces. Point-to-multipoint not enabled by default on any interface type. Interface is advertised as a host route /32 and sets the next hop address to the outbound interface. Primarily used for hub and spoke topologies, like for example the DMVPN. Loopback network type. Default setting on OSPF enabled loopback interfaces. Interface is advertised as a host route. These are the values of the timer, dead interval timer, and wait timer. And this whether the OSPF network type requires the DR or BDR. Let's check or discuss the network type broadcast. Broadcast media such as Ethernet are better defined as broadcast multi-access to distinguish them from non-broadcast multi-access networks or NBMA. Broadcast networks are multi-access in that they are capable of connecting more than two devices. And broadcasts sent out one interface are capable of reaching all interfaces attached to that segment. The OSPF network type is set to broadcast by default for Ethernet interfaces. A DR is required for this OSPF network type because of the possibility that multiple nodes can exist on a segment, and link state advertisement flooding needs to be controlled. The hello timer defaults to 10 seconds as defined in RFC 2328. The following interface subcommand overrides the automatically configured setting and statically sets an interface as an OSPF broadcast type. So you can issue this command IP OSPF network broadcast under the interface, and it can changes or statically sets an interface as an OSPF broadcast type. But for Ethernet, it is broadcast by default. Now let's discuss the point-to-point network type, OSPF network type. A network circuit that allows only two devices to communicate is considered a point-to-point network. Because of the nature of the medium, point-to-point networks don't use address resolution protocol, and broadcast traffic does not become the limiting factor. The OSPF network type is set to point-to-point by default for serial interfaces, HDLC or point-to-point encapsulation, generic routing encapsulation, tunnels, and point-to-point frame relay sub-interfaces. So the point-to-point network type is by default used for interfaces, serial interfaces, generic routing encapsulation, point-to-point frame relay sub-interfaces. Only two nodes can exist on this type of network medium, so OSPF does not waste CPU cycles or DR functionality. The hello timer is set to 10 seconds on OSPF point-to-point network types. Last thing, the point-to-point example. The following command sets an interface as an OSPF point-to-point network type, IP OSPF network point-to-point. A third network type is the loopback network type. The OSPF network type loopback is enabled by default for loopback interfaces and can be used only on loopback interfaces. The OSPF loopback network type states that the IP address is always advertised with a /32 prefix length, even if the IP address configured on the loopback interface does not have a 32 prefix length. Let's give an example here. We already did this example. Let's go to GNS3, router number 1. As you can see here, the state is loop back, but issue this command, show IP Ospf interface loopback 0, loopback 1. Yes, it tells you the network type is loopback and attached via interface enable, not a network statement. And that's it. So to here we come to the end of this video. I hope it's been informative, and thanks for watching.